I want to do one more example of converting to spherical coordinates. So I've got a triple integral here in rectangular coordinates on your screen, and we want to convert this to spherical coordinates. Now you can see that if I were to try to integrate this with rectangular coordinates, gets really messy really fast, right? And so our hope is that by converting to spherical coordinates, it turns into a nicer integral, and in fact it will. All right, so the first thing we want to do is think about what our region of integration is here. So let's look first on the bounds for z. Z is between square root of x squared plus y squared and square root of 18 minus x squared minus y squared. Notice when z equals square root of x squared plus y squared, if I were to square both sides, that gives me z squared equals x squared plus y squared. This is a cone, and so this is going to be the upper half of a cone. And on the upper bound, if z equals the square root of 18 minus x squared minus y squared, again, if I square both sides and rearrange, that says 18 equals x squared plus y squared plus z squared. That's a sphere with radius square root of 18. All right, so what I'm looking at here, at least in terms of z, let's give just a rough sketch, looks like an ice cream cone, right? So I've got a sphere packed on top of my cone. Now let's focus in on the xy limits. So our middle integrand has to do with x, and the bounds on x are 0 to the square root of 9 minus y squared. Again, if I set x equal to square root of 9 minus y squared and square both sides, that's a circle of radius 3, and I'm going from x equals 0 to that circle. So I'm looking just at the top right side of that circle. And then y runs from 0 up to 3. So really, over here in my 3D picture, I'm just looking at the portion of this cone that is in, and sphere, that are in the first quadrant above here. All right, I'm not going to actually sketch that carefully. Well, let's see what we can do. Not much. All right, so we're just sort of looking at this orange piece, right? That's bounded above, let's go a lighter orange down here from 3 to 3. Okay, so let's think about how we're going to convert this to spherical coordinates. Well, let's start with rho. If we're looking at points in here, rho is going to go from 0 to the top of that sphere, right? And the top of that sphere is a sphere with r equal to square root of 18. And remember, x squared plus y squared plus z squared in spherical coordinates is equal to rho squared. So my bounds on rho are going to be 0 to the square root of 18, which is 3 root 2. All right, now let's think about theta. And it might be easier to think about it down here in the xy plane. I'm looking at this right quadrant of the circle of radius 3. So what are my bounds on theta? Theta is going to go from 0 up to pi halves. Okay, so now the tricky part is thinking about phi. So if I take a point here, phi, remember, is this angle from z-axis to the the line that's formed from the origin, whoops, to your point. And so the furthest out that's going to go is out here where the sphere and the cone meet. So I need to figure out where the sphere and the cone meet. Okay, so I have z squared equals 18 minus x squared minus y squared for the sphere, and z squared equals x squared plus y squared for the cone. So let's plug this in to this first equation. So that says that z squared equals 18 minus the quantity z squared. And so if I combine the z squareds, I get 2c squared equals 18. So z is 3. And this is helpful because my formula for z is rho cosine phi. And so I can plug in 3 for z. Rho, if I'm here where they meet, rho is got to be on the sphere, and that's when rho is 3 root 2. So I can replace rho with 3 root 2 cosine phi. And now the cosine of phi, if I rearrange, is 1 over root 2. That's an angle that you should know. That's phi equal to pi over 4. So my bounds on phi are 0 to pi over 4. Whoops. All right, now that I've got all those bounds, I can plug into the formula to convert. So my integral, I'm just going to write over q of, what was it? X squared plus y squared plus z squared. dv becomes, so let's do phi on the outside, so 0 to pi over 4, theta in the middle, 0 to pi over 2, and rho we said went from 0 to 3 root 2. X squared plus y squared plus z squared is just rho squared, and then we need to multiply by rho squared sine phi, and then we have d rho, d theta, d phi. And now this, I hope you'll agree, is a much simpler integral to handle. Okay, I'll let you figure out what you get here. Again, please email me or set up a Zoom office hour with me if you've got questions.